is a fact that nobody actually really asks you to take note of, to notice, and this is one of the most important things of linear operators. So if you have a linear operator, right, a transformation, it acts on the vector x, and it spits out a new vector, the transformed vector y prime. But now, let's say in general, you have a vector x, and the operator acts on it, right? Since it's linear, what that means is you can put it in here, you can put it in the sum, and it will just act on E. So any vector that you act on will just be equal to the coefficients of that vector. And the real thing that the operator changes is not the coefficients, it changes the base vectors. In other words, look, notice, this is the general formula. We don't know what x is. And for any x, if x was, I don't know, h, q, whatever you represent the vector with, whatever symbol you use, whatever vector that is different, it doesn't matter what vector you use, the operator will always act on the base vectors because you can put it into the sum. In other words, the only thing that a linear operator changes will be the base vectors, which means I can find any vector if you just tell me how the operator changes the base vectors, which is not specific to that vector. The base vectors are independent of what vector you're representing. Any vector will be equal to some coefficients which are unique to that vector, but multiplied by something that isn't unique to that vector, which is the E base vectors, right? The E base vectors in a vector space V is not unique to a specific vector. Any vector will include the base vectors E, but it will have specific unique coefficients xi to represent that vector, that specific vector. And so look at this, notice the only thing the operator changes is the EI hats, and the EI hats are general. They are something that all vectors in the vector space V share. What they don't all share are the specific coefficients, because I won't prove it, and it has been proven that every vector in a vector space has unique coefficients. If that vector space, every vector space has unique coefficients, unique to those specific vectors. Every specific vector has specific coefficients, but all vectors, not a specific vector, all vectors will share one thing in common, not the coefficients. The one thing they do share will be the base vectors, right? And that's the key idea. The operator acts on the base vectors, which is something that all vectors share. So if it only changes something which is shared by all vectors, and it doesn't change the thing specific to the vector, what does that mean? It means we can represent all vectors in the vector space, any vector, just by knowing what the transformation matrix, the linear operator, does to EI in general. In other words, what this is, and then just tell me the coefficients, the specific coefficients of that specific vector, and I can tell you what happens to that vector, where it goes, how it transforms. That's amazing. In other words, the only specific thing I need to know about a vector in order to know where it lands is the coefficients that represents it. I don't need to know anything else. This is something that you can tell me in general, and therefore my question will be reduced. For a specific vector, it will only be reduced to the question of what are the coefficients that represent it. That's it. I can do the rest. I need no other information.